faith and how kind of science and faith intersects and are not necessarily opposed to each other. If you don't know, I teach chemistry. I'm a scientist, and this area really kind of interests me because I like science. I think science has a very, very important role to play in society. I think science is like kind of a big deal for us. We get lots of cool stuff from science. We get medicine from science. We get technology from science. We're able to go to the moon and back because of science. And then I'm also a Christian, and my faith is very important to me. And I think the two things kind of coexist pretty well. So first question is, I want y'all to think about this. There is an inherent conflict between science and faith. So what do y'all think about that statement? So show of hands, if you agree with that, raise your hand. If you agree with that statement, there's an inherent conflict between science and faith, raise your hand. Just show of hands here. A few of you guys, not very many. Okay, all right. In a recent Pew survey, about 60 to 70% of folks that responded agreed with this statement, that there's an inherent conflict between science and faith. And what I'm not sure what I'm not sure what you think about when you see a statement like that. Maybe it's that, here's some characteristics of science. Science is empirical, and what that means is that science depends on things that are observable. So things that you can see, things that you can measure, things you can touch, you can hear, you can, depending on senses, things that are observable. For example, if I take this and I let go of it, it's going to fall to the ground, right? We can observe that. That's observable. If I take my cup of water and I raise the temperature of it, it's going to start to boil. That's observable. So science is empirical in that science depends on physical evidence. Science is also reproducible. So one of the very, very basic characteristics of science is that it has to be reproducible. Your results have to be the same as mine. If you take this and you let go of it, it's going to fall to the ground. If I take this and let go of it, it's going to fall to the ground as well. And so that's what we mean by reproducible. It shouldn't depend on who's doing the science. We should get the same results. And science is also falsifiable. And that's kind of a really important aspect of science. Falsifiable means that there's got to be some evidence out there that tells you that you're wrong. Or you've got to be willing to accept some evidence that tells you that you're wrong. So here's what falsifiability means. Big Bang Theory. We have this theory that in science that the universe started with this gigantic bang, Big Bang Theory. And some people object to that and say, well, you weren't around to observe that. We said that science is empirical, that it has to be based on observations. And so some folks will say, well, no one was around to observe the Big Bang, so, that's not science. Well, that's really not what empirical means. Empirical means that there's evidence now that something happened in the past as well. And so if the Big Bang Theory is correct, and the universe started with this Big Bang, then what we do expect to see is that things are flying apart from each other. Does that make sense? So like if you have an explosion, all the little particles in the explosion would be flying away from each other. And if the universe started with a Big Bang, we would expect that all these little particles, or big particles, to be flying away from each other at tremendous speeds. And so that's where the falsifiability comes in. If the Big Bang Theory is correct, one of the pieces of evidence that would support that is, if we look out in the universe, we would see the galaxies are actually moving away from each other. And if we go out there and look at the galaxies, and we see that the galaxies are actually coming towards each other, then we would say, well, that piece of evidence would falsify the Big Bang Theory, because according to the Big Bang Theory, things should be flying away from each other. If the galaxies are actually moving towards each other, then that's where the falsifiability comes in. That's a piece of evidence that would contradict a prediction made by the Big Bang Theory. Make sense? So you have this theory, we're able to make prediction based on that theory, and then we can make observations, the empirical piece of it that says, do our observations fit the theory that we came up with? And it turns out, if we look around in the galaxies, it turns out that the galaxies are actually moving away from each other. And it doesn't matter which direction we look in. We can look this direction, we can look in that direction, we could be on the other side of the world and look away. And it turns out that where we look, the galaxies are moving away from us. So that is evidence for an expanding universe, which fits within the framework of the Big Bang Theory. So in terms of falsifiability, science is falsifiable. If I come up with a piece of observation that doesn't fit within my model, then either my model's wrong or my observation's wrong. I have to go back and I have to fix some things and change my framework. So that's what we mean by falsifiability. Characteristics of faith. I got this out of Hebrews. Assurance of things hoped for. Conviction of things unseen. No empirical evidence, right? And what is seen was not made of what is visible. So I think that's maybe where some folks get the idea there's some inherent conflict between science and faith, and that faith is not based on empirical evidence. Faith is based on something else, things that are hoped for, based on things that are unseen, based on the fact that we believe that the things that we see came from things that we can't see. So not necessarily empirical evidence. And faith is not necessarily falsifiable either. And some people will say, well, you know, my faith has grown because of my experiences and so forth. And that may be the case for lots of folks. But some people have like really, really traumatic experiences and they still have tremendous amount of faith, you know. And so the idea of faith being falsifiable is I think it's kind of questionable here. So I think this may be part of the reason that a lot of people think that there is a inherent conflict between science and faith. What I would like to propose to you today is that that conflict is not necessarily as great as we think. If you look at Romans chapter 1, that text is a little small for you. I don't know if you can read that or not. Romans chapter 1, verses 19 through 20 says, "Since what may be known about God is plain to them, because God has made it plain to them. For since the creation of the world, God's invisible qualities, his eternal power, divine nature, have been clearly seen, and being understood from what has been made, so that people are without excuse." There's a couple of different ways to interpret that passage, but one way that I look at this is to say that God has made himself evident to us through his creation. And the study of his creation is part of what science does. We look at the natural world around us. We look at biologists look at the things that are living. Chemists look at the things that are not living. Physicists look at, you know, how objects, how things move and so forth in the universe. And a lot of science is a study of God's creation. And Paul tells us in Romans that if you look at his creation, God has made himself evident to us through his creation. So what I want to suggest to you guys is that that conflict that we may perceive that maybe exists between science and faith, I think is not quite as great as some people may think. That if we really kind of take a impassionate view of the world around us, God has made himself evident to us through his creation. Now, when some people read this passage, or when you read this passage, what do you think of? This is tough to like have a dialogue, so let me guess at what you think of. A lot of people will think about maybe the sunset, right? And then you sit and you look at the sunset and you look at the colors of that sunset and you think about the magnificence of that sunset and that, wow, You know, God did a good job on that. And some people applaud and clap their hands and say, good job, God. Like, you know, that was a beautiful sunset. It was amazing. Some people will think about the intricacies of life. The fact that our human body, lots and lots of little things that work here, and to kind of imagine all this happened by accident is very, very difficult for folks of faith to say that, you know, all this happened by accident. Some people will say, you know, the tenderness that one person, that a parent would show to a child, that type of relationship, that is evidence of God. And so I think that all those are perfectly valid. There are lots of folks that can explain via purely science without the necessity of having a creator why that sunset is so beautiful. That sunset is beautiful because as the sun is coming across the earth, you know, we have the atmosphere. As the sun is setting, the light of the sun is traveling through the thickest part of the atmosphere. When the sun's right on top, imagine the earth is a sphere right here. When the sun is on top of that, it only travels through a tiny amount of the atmosphere, so the light doesn't get diffracted as much. When the sun is setting, it travels through a much thicker portion of the atmosphere, so the light gets diffracted more. And if you add some clouds in there, add some water vapor in there, that will cause the diffraction of light to be even greater, and that's why we see the colors that we see. So we don't need God to have a beautiful sunset. It's all about physics and light. The human body evolved over millions of years, and these systems that we have is through the process of natural selection. We don't need God for natural selection. You know, if you have characteristics that make you better suited to survive an environment, then you'll survive, and those traits get passed on to your offsprings. If you don't have those characteristics, you won't survive, and you die off, and those traits are not passed on to characteristics, and generation after generation after generation after generation of that happening, our bodies are engineered, quote unquote, engineered to survive in this environment because we possess the qualities that allows us to survive in this environment. We don't need God for that. We have evolution. And then the idea of a parent and a relationship with a child is because, evolutionarily speaking, we want our genes to be passed on. We need, you know, that's just kind of wired within us that we want our genetics to be passed on. And because our genetics allows us to survive, we want those genes to be passed on. And so that's why we take care of our kids. We don't need God for that because it's just it's an evolutionary trait that allows us to kind of, you know, to care for our children, have this special feeling towards our kids, and because of that, that's why we have those tender feelings towards our kids. We don't need God for that. So there's, you know, all the things that we kind of mentioned. There's a quote unquote scientific explanation for that doesn't involve God. But there's a challenge for those scientists, and what I want to present today is a challenge for the scientists that says, you know what, all this stuff exists. We can explain why the universe exists from a purely naturalistic point of view without the presence of God. And the argument I'm going to make is coming from the perspective of a fine-tuned universe. A fine-tuned universe. The fine-tuned universe says that there are some physical constants that exist within the universe that allows not just life to exist, but for the universe to exist. Not just that we're here and we have the ability to think and reason and to have logic, the capacity to love, the capacity to care for each other. Not just that we're here, but the universe exists. The universe exists because of some very, very interesting things that happened at the very beginning of the universe. And there's no explaining this. There's no, well, you know, evolution took care of that. There's no, well, the physics of it is because of this. There's no way of explaining why the universe exists because of these very, very fundamental facts that exist within the universe. There's lots of these, okay? I'm just going to touch on 3 of them because, we don't have, I have one session to do this, so I'm going to touch on 3 of these. And if you want to kind of go back and you go on and go in detail and really kind of think about the other parts of this, I welcome you to do that. Well, I'm going to touch on 3 of these, okay? So the 3 things I'm going to talk about are the force of the Big Bang, the universal gravitational constant, and the nuclear fission constant. And I can see like eyes glazing over already. Oh man, what is he doing? The universal gravitational constant, what is he talking about? I promise you, I hope, well, I'm going to do my best to try to make it as relevant as possible. I don't know if I can keep that promise, but anyways, let's talk about the Big Bang, okay? Big Bang. When Kurt started this series a while back, he said that, there's 2 different schools of thought about old Earth versus new Earth. And, the Earth is either several million years old or if it's 6,000 years old. And he said that, really we don't need to talk about that. If you want to believe that the Earth God created the Earth 6,000 years ago, and the analogy I heard is that when God made Adam, how old was Adam? I don't know. Was he a newborn baby or was he a grown adult? I don't know. And if he was a grown adult, when God made Adam, could God have created a universe that was like, 14 million years old when he created the universe? Well, sure, he could have. But what I'm here to tell you is that the empirical evidence, remember, as a scientist, I deal with empirical evidence, things that we can see, measure. The empirical evidence points to the fact that the universe is about 14 billion years old, and it started with a Big Bang. Now, when I was in high school, I didn't like the Big Bang because I thought, well, God created the heavens and the earth, and that's the way it was, and I didn't like the Big Bang, and I tried to reason my way. Well, the Big Bang, there's a ton of evidence that says the Big Bang happened 14 billion years ago, and now I'm thinking, hey, that's pretty cool, because the first passage in my Bible says, in the beginning. In the beginning. Which the Big Bang tells us there was a beginning. Because there was until about 30 years ago, there were some competing theories about how the universe came into existence. One of the theories was called the steady state theory. That is, the universe has always been and always will be. They couldn't explain how the universe began, so scientists came with the idea, well, the universe has just always been. It's always been here, and it's always going to be here. So that's called the steady state theory. Well, nowadays, we know that because of the observations that we make and so forth, and by the way, if you listen to your radio, if you have an old-timey radio and you tune it on no particular station whatsoever and you hear static, that's the cosmic radiation, background radiation from the Big Bang explosion. Pretty cool. And so 14 billion years ago, there was a beginning, and the universe came into existence. And you know this guy called Einstein, his theory of relativity, he says space and time are related to each other, theory of relativity. Time cannot exist outside of space. And when I space, I don't mean like planets and stars, I mean like space. Time cannot exist outside of space. Without space, without the universe, there is no time. So it's not as if time has been chugging along all this time, and all of a sudden, somewhere along this timeline, boom, the universe came into existence. And it is that time and space have to coexist with each other. You cannot have time without space. So there was, if you look at the timeline of the entire universe, there was a zero when time started. Way back when, there was a zero when time started. In the beginning. There was a beginning, not of just the universe, but there's a beginning of time as well. The universe is still expanding. There's something called the red shift. You know, like if you're sitting on the side of the street, you know when the fire truck is coming towards you, and you know when it's going away from you, right? How do you know? The tone, right? The tone of the siren. That's, yeah, anyone know what that's called? Doppler effect, that's right, Doppler effect. So when something is coming towards you and it's emitting sound waves, those waves get compressed, so the tone goes up because the frequency gets higher because the wavelength gets shorter because that object's moving towards you. And when it's moving away from you, the wavelengths get elongated and the frequency drops and you get a lower pitch. So you can hear when something is coming towards you and you can hear when something's moving away from you. We do that with sound. The very same thing happens with light. If you have a source of light that's moving towards you, it's going to cause the wavelength to get shorter, the frequency to go up, and that's called a blue shift because blue light has a shorter wavelength and a higher frequency than normal light. Or blue light has a higher frequency and shorter wavelength. Red light has a longer wavelength and a lower frequency, so when objects that are bright are moving away from you at a high rate of speed, you'll see a red shift. And what I mentioned earlier is that no matter where you look in the universe, there's a red shift. All the galaxies are moving away from us. How is it possible? I mean, why isn't there one galaxy moving towards us? Because the universe itself, space itself is expanding. The universe itself is getting larger and larger and larger and larger. So, I don't know about you. As a Christian, I'm pretty excited about the Big Bang because it tells us that, there was a beginning. And in that beginning, there was an explosion. So, it didn't really look like this. This was the best way I can kind of think to represent this, okay? So, we have a bomb there and it explodes up. We kind of understand that, right? And then, if I wanted to control the size of the explosion, what would I do? Well, I would change the amount of gunpowder I put in the cannonball on the left-hand side, right? So if I put a small amount of powder in there, I get a small boom. If I put a large amount of gunpowder in there, I get a big boom, right? Everyone understands that, okay? All right. So one of the first pieces of evidence that we have that the universe didn't just come in existence by accident is that the size of the boom matters. The size of the Big Bang matters, okay? So now that we've established there's a Big Bang, okay, the size of the bang matters because if the Big Bang was too big, if the bang from that Big Bang was too big, imagine all the stuff in the universe, everything in the universe used to be like in this, it's hard for me to, all matter was like in this little tiny amount of space right here. And then in a fraction of a second, it just went boom. And you can also ask, well, where did that boom come from? And, that's a different story. So in a fraction of a second, all that stuff went boom. And if that boom was too big, then imagine all these particles shooting out at a really, really, really rapid rate of speed. And they just start flying away from each other. And the galaxies never get a chance to form. Because galaxies depend on gravity. It depends on gas molecules, gas particles being attracted to each other, stuck together, make stars. Stars then are attracted to other stars, and so forth. If that bang of the Big Bang was too strong, too large, if we put too much charge, too much gunpowder in that first, in that cannonball, then everything would just fly away from each other and just keep flying away from each other, never coalesce into to stars or planets or molecules. If that bang of the Big Bang was too weak, if we didn't put enough charge in that cannonball, then as soon as it kind of went boom, then gravity would take over and would come right back together. And when I say right back together, the expanse of time is like billions of years. So we're not talking like, oh, all of a sudden, 2 seconds later it comes back. But the fact that we are here today, the fact that the force of the explosion was just right. Sound like Goldilocks here. Can't be too big, can't be too small. The force of the explosion has to be just right so that the molecules that were formed in initial hydrogen atoms that were formed right at the initial of that very, very beginning of the existence of the universe don't just keep flying away from each other. They were actually had an opportunity to attract each other through gravity, to form stars. Those stars then form galaxies, and then they spin off and form planets and so forth. That force of the explosion had to be just right for that. And those particles didn't just come back together, and that was it, end of the universe as we know it. So the size of the bang matters. So first thing is, without God, we had to depend on luck, right? Without God, we had to depend on luck to make sure that the bang and the Big Bang wasn't too strong, and the bang of that Big Bang wasn't too weak. So that's the first thing I want you guys to consider, is that the Big Bang, even if we kind of can't wrap our brain around that 14 billion year thing, the bang of that Big Bang had to be the right size, the right amount of force in order for the universe to exist as we know it. The second thing is gravity. 2 bowling balls up there. There's a gravitational attraction between those 2 objects. In fact, Newton tells us there's a gravitational attraction between any 2 masses. And you have 2 bowling balls there. There's a gravitational attraction between those 2 bowling balls. And bowling ball on the left is being pushed towards the bowling ball on the right. And the bowling ball on the right is also being pushed to the bowling ball on the left. I didn't have enough room, so I only showed one of the forces on there for physics folks. Only one of the forces is being shown on there. All right. I have 2 tennis balls up there. 2 tennis balls also exert a gravitational pull on each other, okay? Now, normally we don't think of 2 bowling balls as being pulled towards each other because that force is really, 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 really small. And we are bound by gravity, not because our mass is really big, because the Earth's mass is really, really, really large. And so the Earth exerts a force on us. We call that weight. So that force that the Earth exerts on us is what we weigh. So any 2 objects that has mass are going to be attracted to each other by gravity. We typically don't think of gravity unless it's on a really large scale, but they exist, okay? So why am I talking about that? Because the force of gravity depends on a couple things. It depends on the 2 masses. So if you look at that equation up there, oh man. M1 and M2 represent the 2 masses, okay? So if you have 2 bowling balls, the masses are going to be larger than if you had 2 tennis balls, so the force of gravity is going to be stronger. And then the bottom of that equation is the distance between them. Now, when you divide by a big number, what happens to the value? It gets smaller. So that means that as the distance between 2 objects gets farther away, the force of gravity is going to decrease. So that's what that means, okay? Now, all that is like, well, who cares? What's important is that G. That is called the universal gravitational constant. Okay? Y'all know there's a difference between weight and mass. Do you know that? Weight and mass. Okay. Weight is the effect of gravity on me. So like, for example, I'm sitting here on Earth, and my mass is going to be M1 up there. The Earth's mass is going to be M2 up there. You know, and then there's the universal gravity. And then the force that I wind up with when I do that calculation is my weight. If I go to the moon, my mass doesn't change. I still have the same mass. The moon's mass is 1/6 the mass of the Earth. So the second M is going to be not as big. So what happens to my weight on the moon? It's going to be less by a factor of 1/6. So if I weigh, 180 pounds here, I'm just trying to think of a number that can be divided by 6 easily. So if I weigh 180 pounds here on Earth, I go to the moon, the mass of the moon is only 1/6 the mass of the Earth, so what's the force going to be exerted on me? It's going to be 1/6 as much, so how much do I weigh on the moon? 30 pounds, that's right. So I weigh 30 pounds on the moon, which is kind of cool. Not that it's a really good place to live, but you know what? So now the G part, though, that's the important part. G is called the universal gravitational constant. That is the constant that we multiply the masses by. Make sense? So to figure out the force of gravity, I take the two masses and multiply by that universal gravitational constant, which comes up with the strength of the force that's going to be applied between those two objects. Okay? And we figured out that number. Scientists have figured out that number, and you can actually, they figured, I only wrote down like, you know, to the 5 decimal places. You can write that thing out all the way to 10 decimal places if you want. We've measured it really, really carefully. We know it really, really well, but we don't know where it came from. I mean, it just is, right? There's no reason for that number to be what it is. It just is. It just is. Well, here's another Goldilocks moment. That number has to be just right. Because if that number is too big, then what happens to if that number is bigger, then what happens to the force of attraction between those two particles? It gets stronger, right? If that number is smaller than what it is, then the force of attraction is going to be weaker, okay? So after the Big Bang, hydrogen atoms are flying away from each other. So you got two different things going on here. You have the particles flying away from each other because of the explosion, and then you have those particles starting to reconnect with each other because of gravity. Make sense? So if that number is too big, then these particles will start collapsing on itself again, and then the result is, well, the universe will collapse on itself. If that number is too small, then those particles don't have enough force to attract them so that they start forming stars again. So that universal gravitational constant, which exists, there's no explanation for why it's that number. There's no like, oh, this is the reason that it just is. And if that number was either too big or too small, the universe as we understand it to be would not exist. So another Goldilocks moment. All right, one more thing. And we're going to speed it up here because we got coming up on a time crunch here. Combustion versus fusion. I brought a visual for us here. Can y'all see that? It's a lighter. It's a flame up here. I think it's kind of cool. All right. There's a chemical reaction that's responsible for producing this energy right here, the heat energy that we see here. There's a chemical reaction that's responsible for that. Butane, which is what is commonly known as lighter fluid, is the stuff that's in here. When I let it out, the butane is combining with the oxygen, and there's a chemical reaction, and the chemical reaction produces two things, carbon dioxide and water. Now, if you're a chemistry person, you look at that and say, wait a minute, that's methane on the left-hand side. That's not butane. I know, okay? I was trying to keep it simple. So that reaction that's up there shows the chemical reaction between a hydrocarbon, either butane or methane, combines with oxygen, makes carbon dioxide and water. Now, what's important in that is I want you to notice that there's a couple elements on the left-hand side of the equation. What are they? Carbon, oxygen, and hydrogen. So you have those three things. You have carbon, hydrogen, oxygen to start with, and then you wind up with what? Carbon, hydrogen, and oxygen. The only difference is that the way they're arranged is different, right? On the left-hand side, the carbon is stuck with the hydrogens, the oxygens by themselves. On the right-hand side, the carbon's stuck with the oxygen and the hydrogen's stuck with the oxygen. So the way these atoms are arranged is going to be different, but you have the exact same atoms, the exact same number of atoms. This is called the law of conservation of matter. Law of conservation of matter says that matter cannot be created or destroyed in a chemical reaction. So if I were to take this lighter, if I let this burn for a while, the lighter's going to run out because the butane's going to run out. Where'd the butane go? Well, it turned into carbon dioxide and water. So if I were very, very, very careful, I measure the amount of butane, the amount of oxygen that I had to start with. I measure the amount of carbon dioxide, amount of water that I wound up with. What you'll find is that they have the exact same mass. You can't make matter disappear, okay? Law of conservation of matter. So that's chemical reaction right there. That's just this is not what's happening in the sun. This is not, some people think, well, the sun's just a great big fireball in the sky. It's not a great big fireball like this in the sky. There is something very, very different happening in the sun. And what's happening in the sun is called a nuclear fusion. That's the reaction that's taking place in the sun. What I want you to notice is that what's on the left-hand side of the equation? Hydrogen. What's on the right-hand side of the equation? Helium. We made a new element. That's the difference between a nuclear reaction and a chemical reaction. A chemical reaction, matter is conserved. A nuclear reaction, matter is not conserved. Some of that stuff actually turned into energy. Einstein, E is equal to mc squared. Y'all know that one? E is energy. M is the mass of the substance that gets turned into energy. C is the speed of light. Speed of light is a huge number. So a tiny amount of energy can turn into, a tiny amount of mass can turn into a great big amount, huge amount of energy. And that's the difference between a conventional bomb and a nuclear weapon, right? So if you think about in terms of like our military, we have conventional bombs, which is like dynamite and stuff like that. You drop that, it goes boom. That's just a normal, conventional chemical reaction that causes that boom. You have a hydrogen bomb or an atomic bomb, matter is actually converted into energy. Totally different process. The end result, though, is that you still get a lot of energy out of it, but a small amount of matter will give us a huge amount of energy. Well, it turns out that the amount of matter that gets converted to energy is 0.0007. It's 0.0007. That is, if you start out with 100 grams of hydrogen, you're going to wind up with 99.3 grams of helium. What happened to the 0.7 grams? It got turned into energy, a large amount of energy. Where'd that number come from? Just the way it is. Just the way it is. And it's a good thing that number is 0.0007. Because if that number was smaller, then hydrogen atoms would be bouncing into each other and they would just go uncontrollably into a reaction. I'm sorry, if the number is bigger, you get a whole lot more energy out of it, and then hydrogen atoms just constantly bouncing into each other, and you just get an uncontrollable reaction, and basically all the hydrogen in the universe will be consumed very, very quickly and get turned into energy. If the number is smaller than 0.0007, then what would happen is that the reaction wouldn't occur. There's not enough energy to sustain that reaction. That fusion reaction takes a lot of energy. You got to have the sun to do fusion, right? You got to have a tremendous amount of energy to keep that going. And if we don't get enough energy out of that process, then there's not enough to kind of keep the process going. So again, the Goldilocks moment, right? 0.0006 too small, 0.0008 too big, 0.0007 of the matter that gets converted just right. How'd that happen? Science doesn't have an explanation for that. There's no like, well, this is it just is. The things that we just talked about, the force of gravity, or the force of the Big Bang explosion, the universal gravitational constant, the amount of matter that gets converted to energy are just the way it is. They're just the way it is. And so, what's the conclusion that we can draw from this then? Well, scientists, sometimes we're kind of stubborn. Some scientists have come up with this idea of a multiverse. So our universe is one of many, 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 many universes that can be out there called the multiverse, okay? And they've worked it out on paper and stuff and said, hey, it's possible. That's great. Problem is that, remember, science is empirical, right? So what does empirical mean? Got to be able to measure it, see it, you know, and so forth. And there is zero evidence for any other universe than our universe. that we've been able to observe. That may change in the future, but as of right now, there's zero evidence that there's any universe out there that's not part of our universe. There's no evidence of a multiverse in other dimensions that have other characteristics and so forth. So their explanation is that, well, maybe there's like a million multiverses out there. Ours is one of this million. And in our universe, the constants are such that the universe exists and life is possible. You know what we call that? Faith, right? That's called faith. Or the other part of that, the other explanation is that there's a creator. There's a creator that fine-tuned the universe so that it is able to exist and host life. And again, this is just 3 different things that we talked about. These are only 3 different things. There's a multitude of things that you can look at if you want to get into the study and think about, you know, water is bent. And the reason that water is bent is because of the orbitals around the oxygen. And why are the orbitals that way? Well, we don't really know. But water's bent. And that allows life to exist. If water is linear, if water, you know, water looks like a Mickey Mouse molecule, oxygen in the middle, 2 hydrogens out here, it's bent. If it was linear, if it was just oxygen, hydrogen on this side, hydrogen on this side, life wouldn't exist. The difference between 180 degrees, 105 degrees is the difference between having life on Earth and not having life on Earth. Kind of cool. So water, there's all these little pieces of evidence out there from that doesn't require, you know, that's not open to like interpretation. That's not open to like, oh, you know what, this occurred because of the, you know, evolution or something like that. There's just some fundamental constants that we see in science that says, if you want to believe all this happened in an accident, you can do that. But it takes a lot more faith, in my view, to believe that than to believe that there is a creator. All right, we need to finish up here, so let's have a prayer. Father, we thank you for this day that you've given us. Thank you for all the blessings that we have through you. And Father, we praise you for making yourself and revealing yourself to us through your creation. And Father, we honor that. We're so humbled by your presence here, and we just thank you for being part of our lives. Thank you for your Son. Through his name we pray. Amen.